Okay, 7.3, let's talk about the number E. It's known as Euler's number. That's how you pronounce Euler. Some famous mathematician, don't know much more than that. A lot of us in Algebra 1 learn this fundamental interest formula, that the amount you have at the end is equal to your principal, what you start with, times 1 plus your rate, and raise it to the number of times it gets to grow. If it's annually, this tends to be pretty much the formula we use. But in 7.1, when you're looking at exponential growth, you learned the compound interest formula. So if we compound things quarterly, we have to divide the rate by 4 because we're doing it 4 times a year, and each quarter you've only earned 1/4 of that annual rate. And then therefore, if it's been 5 years and we've done it 4 times per year, that would be 20. If we're compounding monthly, n is 12. If we're compounding daily, n would be 365. If we're compounding continuously, meaning it's happening all the time, then n is infinity. So let's see what happens to just this part of the equation. When we have 1 plus 1 over n raised to the n, so I'm just looking at this part, I'm taking out your start value and the number of times it gets to grow. And I'm just going to change it to x's to make our lives a little simpler. What's going to happen as x goes to infinity? Well, on the calculator, I graphed 1 plus 1 over x raised to the x. And then when I press graph, you can see that it grows and then eventually levels off. This is sort of the curious thing. And if you can see the value there is, you can't quite see that, but turns out to roughly become 2.718. So Euler's number is truly just a number. It's approximately equal to 2.718. Sort of a curiosity. Now from this, and this is a little bit of a derivation, you don't totally need to understand it, but I like to throw it out there, we're going to get the compounded continuously formula, which we also use a lot in biology because it's not like cells just decide to reproduce once every hour. It's happening continuously. Later we're going to refer to this as the natural base because it's what occurs in nature. So here I go to my compound interest formula. And I'm just going to do a little finagling to get to where I want to. If I flip this, 1 over n over r is r over n, right? Dividing by a fraction is like multiplying by the reciprocal. So I've just took some liberty to write this as 1 over n over r instead of r over n. And then instead of n, I'm going to write n over r, but then I'm going to raise it to the rt. So remember, we multiply when we raise an exponent to an exponent. So that r would just cancel that r and would be back to nt. So this is just a re-expression of this formula, taking liberty to reorder things a little. So what happens if I let n go to infinity? Well, I'm just going to get infinity over r, which is just infinity. So here's my 1 over infinity. And again, infinity over r is just infinity. So here's my 1 plus 1 over infinity going to infinity. Here's my 1 plus 1 over infinity going to infinity. And we realize that that number is just 2.718, or e. So instead of this, I can just write e. And then I get the amount that I have at the end is equal to what I started with times e, Euler's number, raised to the RT. So that's where that compounded continuously formula comes from, and that's a little bit about e. It's this function as x goes to infinity, which curiously enough levels off to about that value. E, again, is just a number. You can almost treat it like a variable when you're using exponents and simplifying with e. E to the 7th times e to the 4th, same base, add the exponents, e to the 11th. 2e to the negative 3 times 6e to the 5th. I can do multiplication in whatever order I want. 2 times 6 is 12. E to the negative 3 times e to the 5th is just e squared. Rules when you have a quotient. 24 divided by 4 is 6. E to the 8th over e to the 5th. Just subtract and you get e to the 3rd. if I have 10e to the negative 4x and raise that to the third, the 10 gets raised to the third, that's 1,000. Multiply exponents, e to the negative 12x. Again, what does a negative exponent mean? Put me in the denominator. So this becomes 1,000 over e to the 12x. So you'll have to do some simplifying with e. And then graphing. So they don't really give you, we talked about graphing in 7.1, a times b to the x. I'm going to throw this in there, a e to the rx. So if I have a function y equals 3e to the negative 2x, again, 3 is my start. Maybe I start with 3 cells. And this negative indicates that I've got decay going on. So maybe it's grams of carbon or something. Because that rate is negative, I've got decay. Let's make a quick table of values. So negative 1 would be 3e to the positive 2. That turns out to be about 22. How do I do that on my calculator? So you do have an e to the something button. I'm going to clear all that. I don't know how well you guys can see this, but I would do 3 times, and then over here above the natural log, because that's the natural base, if you hit second, you get an e to the, and then you can just plug in your 2 and hit return, and it tells me that 3e squared is 22. You have to do some problems on your calculator. If I plug in 0, anything to the 0 is 1. 3 times 1 is 3. If I put 1 in there, oops, that will be 3e to the negative 2, which will be 3 over e squared, which we know is less than 1. And if I put 2 in for x, I would get 3e to the negative 4, which would be 3 over e to the 4th. So yeah, that's 2.7 to the, so that's less than 1. I'll do that one. 3 divided by second e to the 4th, yeah, is 0.05. So yeah, things are getting pretty small. I start up here at negative 1, at 22, at 0 I'm at 3, at 1 less than 1, and at 2 I'm at 0.05. So there's my exponential decay. So that should help you get through 7.3, Euler's number.